So this is Unit 3, Quiz 1. Really could be Unit 3 test. This is really everything that's in Unit 3. Talking about energy, energy transfer, how it affects substances, how it affects particles. So we have to use our knowledge of different phases. Sorry about that delay on the video on Google Classroom. It was something really, really important. Um, so the three things that we've done so far, that's what your quiz is tomorrow. So first of all, the first thing we started the semester with, so part one, was the graphing. So you need to be able to graph. You need to include everything on the graph that you should include. So what things should we include? Starting from the top down, starting from the setup to finish. First thing I'm going to have to do is I'm going to have to title the graph, right? We always title our graph. We have to label the axes, which seems pretty simple, but not really, because we have to do a couple things here. We have to determine what we want on each axis. I know that looks like axes, but it's also axes, which is axis plural, rather than axes. Because the x-axis, if you remember the dry mix thing, but the dependent variable should always go on the y-axis, and the manipulated variable should always go on the x-axis. So that could be important. What we did in class was we did a relationship between, mass and volume. And so you could have said to yourself, does the volume depend on the mass or does the mass depend on the volume? And either way, you could really say it's acceptable. It sounds acceptable. And then I had you put mass on the y-axis just because it worked out better for the relationship. Because the relationship that we did was density, the relationship between mass and volume. On your quiz tomorrow, it's not going to be that same relationship. It's going to be some other relationship, and you can figure out what you want to put there. All right? Also, when you label the axes, you want to make sure that you include units in parentheses. Okay, so I'll be looking for that. It's going to be a stickler for detail on setting up your graph. You guys should know graphing. I mean, you've been doing it since like 3rd grade, right? But now we got to pay attention to the details. You have to know how to make an appropriate scale. Okay, so if I have all this room available to me on the graph, don't make it so that your plotted points are all like right here. Okay, use the majority of the graph. You don't have to make it take up the whole perfect right along the edges. Okay, but you should use at least like 3/4 of each. All right. One way of doing that is if you take whatever your range is. So saying I got to go from 0 to whatever number of units. Okay, I got to go up to say 200. Okay, I got to cover up to 200. It's always a good idea to kind of shoot a little bit above your highest value. And then how many marks do we have? Because a lot of times I'll give you a graph with marks already on it. Okay, so how many marks do I have along that axis? If I take that number of units that I need to cover and divide by the number of marks, that gives me a rough idea of what the value of each mark should be. A lot of times it comes out to be some weird decimal number, and that's okay. But if you do get a weird decimal or a weird number, like 7 or something, maybe you don't like 7 or 8, I don't want to make each mark worth 8 because it's weird. Just round up. Always round up. And round up to some kind of normal number. All right? And if you have pencil, you can always try a few different things to see if they work because you can erase. Okay? No thanks, I'm good. So once we have that all set up, we need to obviously be able to plot points. What is the x value? What is the y value? So what is the x value? What is the y value? Where do they meet? Okay, I'm going to put a point there. Plotting points, x and y. This is the x value. This is the y value. All right. Once we have the plots pointed, just like we did in our practice, we are going to have to make a best fit line. You got to understand that when you do a best fit line, what you're trying to show is an average or a trend, really a relationship between the two variables that you're dealing with. Okay? So when we do a best fit line, we have some points plotted here. What we want to try to do is we want to start at the origin and try to go make a line so that it has an equal number of dots on each side. And they're not all going to be exactly the same when you guys do best fit lines. We want to try to do something that goes right through the middle of our data, something like that. Okay? So that would be acceptable. That would be acceptable. That would be acceptable. What wouldn't be acceptable is like that. What? What is that? Okay? It's a line. It's not a best fit line, though. All right, the idea is that when you have this best fit line, that represents the average relationship between the two variables. Okay? We can even put a number on that by finding the slope. And the slope, so that's the next thing we got to make sure we can do is slope. That's rise over run. Rise is just the change up and down. How much does it change up and down? And the up and down axis is the y-axis. So how much does the y change? So I'm going to put triangle y, which really stands for delta y, which really means change in y. Whenever you see triangle in math or science, well, I guess not always in math, not in geometry. But if you see this triangle, it's the Greek symbol delta, and it represents change. So this means the change in y divided by the change in x. Okay? It's another way of putting it. The other thing we did was just start from left to right as you're going along the best fit line. Find a couple of marks that are easy to read in terms of x and y values. What we'd call this first mark, that would be our x1 and y1. The second mark would be x2, y2. So if we wanted to do that, we could just say y2 minus y1 divided by x2 minus x1, and then we get our value for the slope. So this would be x1, y1 right here, and this one would be x2, y2. So once you've got that number tells you the relationship with an actual number, all right, with an actual quantity. Any questions about that? So that's part one. Part two of the quiz is going to be phase change diagram. And what you're going to get is just something like this. Might not be exactly like this, but something like this. Okay? And you're going to have to know what that represents, all parts of it. I might ask you, What part of this graph is a solid? In which case you would want to say something about this part being a solid. All right? I might say which part of this graph shows a liquid particles beginning to vaporize. Okay? So that would be here, right? This is vaporization, right? Okay. This is liquid. This is gas. So we need to understand here that wherever there's plateaus, wherever there's flat spots, that's where a phase change is going on. So if I'm going left to right, what I'm doing is adding energy. And this side is the temperature, usually in degrees Celsius. And so we see that this is a solid, really it's getting warmer. And so understand a couple things that we talked about that actually tie into part 3 is this and this. Thermal energy and phase energy. Okay, so with this solid down here, if the temperature is going up, that's like the thermal energy. It's related to the motion of the particles. So here, I have particles in a solid moving faster and faster and faster. We should also understand like the properties, how are particles arranged in solid, liquid, and gas, how fast are they moving, which one has the most energy, which one has the least energy. Um, we should also understand that solids, liquids, gas in terms of definite shape, definite volume, or indefinite shape, indefinite volume. Indefinite shape, definite volume. You should know those. Solid is definite volume and definite shape. Doesn't change regardless of the container. Because the particles are all close together, there are strong interactions between particles. And so at this point, we're still adding energy, but the particles are not moving faster. Otherwise, the temperature would be going up, right? So here, it's going through a phase change. The only thing that's changing here is the phase energy. And we call that phase change between a solid and a liquid, we call it melting. And when all the particles have gone through that phase change, now they're all arranged differently like a liquid. Okay, now they're going to move faster. They're going to spread out a little bit more from each other, take up a little more space, continue moving faster and faster and faster until they go through another phase change. So again, the added energy is making them turn into a gas particle arrangement, not move faster. All right? Then when they turn into a gas, if we still kept the track of the temperature of the gas, we'd see the particles move faster and faster and faster. Cam? All right, so we also got to understand it going the other way. If I've got these gas particles spread out, a lot of energy, they're moving really fast. If I can get them to transfer some of that energy to something else, then that energy transfer will cause them to cool. So they'll move slower and they'll come close together until they start to turn into a liquid, which we call this point the condensation point. And so what we see here is that the condensation point and the vaporization point are actually the same thing, just depends on the direction you're going. And if I said, what is that point for this substance, all you got to do is go across from there and say, oh, it's about 60. Okay, so this substance, when it reaches 60 degrees, it's going to go through one of those two phase changes depending on what the initial state is. Okay? Then it turns into a liquid, and those particles start moving slower and slower and slower and slower until they start to come together as a solid, which we call freezing. Okay? And while it freezes, the temperature shouldn't change. The energy being released is just causing them to go into the solid phase. Once we get to the solid phase, then we can continue to make them vibrate back and forth slower and slower and slower. Okay? So understanding this is very important to what we're doing. That and understanding this. Q. What is Q? Does anybody remember what Q is? Heat. Right. Okay? It's heat. We talked about a few ways that energy can be transferred. In physics, they deal a lot with the energy transfer through mechanical means, larger objects, doing work. In our class, we talk about heat transfer, Q. You have to understand what this really means on the particle level. Because if you remember on that handout, I briefly described what each energy transfer type was like. W, Q, and R. We're just dealing with Q because what that is that's energy transfer because of collisions between these tiny, tiny particles. So if we understand that energy is being transferred from the system out to the surroundings or the other way around depending on the process, understand it's because of collisions. If I'm heating water, it means that the energy from whatever's causing the heat is getting transferred to the water. So that has more energy than the water does, and the collisions are causing a transfer of energy to the water. That's then going to speed up those particles. Okay, they're gaining energy, they're speeding up. But understand it's collisions, because I'm going to have you explain that on the quiz tomorrow. Collisions transferring energy. You just need to know what's the system. Is it transferring energy out of the system? Is energy getting transferred into the system? What is it? And that leads us to our third part, which is the LOL charts. Okay? With this, though, I could be able to ask anything like what is the melting point? What is the freezing point? What is the boiling point? What is the condensation point? Any of that is fair game. We'll see how that goes. All right, so part 3, the LOL charts. Okay, another delay while I pass out Unit 3 Worksheet 2. But I want to practice these some more and think about these in terms of system and surroundings. This is meant to show us conservation of energy and matter, by the way. So conservation of energy and matter means that energy cannot be created nor destroyed, right? It can be transferred, and that's it. So we have our LOL chart. We call it LOL because it looks like a big LOL, lol, okay? We have this representing the initial and this representing the final. And this in here represents the system, the circle does. So in number 1, it says, some of the water you spilled on your shirt evaporates. Okay? So, what is the system in this scenario? Water. Okay, so I'm going to write that in here. All right. So water for the system, we're talking about water either gaining energy or losing energy. What's going on? All right, we have some E's listed across here. Really, we just pay attention to the first two, the ETH and the EPH. which stands for thermal energy and phase energy. Thermal energy being like the temperature change, and phase energy deals with the phase. So same thing over here. We don't even need to worry about ECH really. Okay. Um, there are 4 basic norms that we have to use for these charts. We have to understand, first of all, the phase energy. So for phase energy, we use 1 block, 2 blocks, or 4 blocks. We never use 3 blocks. Well, what that represents is solid, liquid, and gas. And that's meant to show that solids have less energy than liquids. Liquids have less energy than gas. Gas has the most energy. Those are really spaced out particles moving really quickly, moving fast. We draw those with like big arrows and stuff. The other thing to keep track of is with the thermal energy, we just kind of stated that this means if we use 2 blocks, 2 blocks is like room temperature. Okay? All right, so I think it's easiest to always just start with the phase energy. So if liquid, we're talking about liquid water at the beginning. So what's the phase? Liquid, okay, so a liquid is 2 blocks. So under phase energy, I'm going to make 2 blocks. Okay? What about at the end? What's it turn into? Turns into a gas, water vapor, right? Water vapor is a gas. So I'm going to make 4 blocks. Now what about the thermal energy? Must have added some, right? So do we want to say the water started at room temperature, maybe a little cooler than room temperature? What do you guys want to do? Room temperature, okay. So room temperature would be 2 blocks under thermal energy. And these might be different. Again, these models might be different. You might have shown it starting at 1 block. Maybe you thought the water was colder than room temperature. That's okay. They don't have to all be exactly the same, but you got to be able to explain the concept of what's going on. All right, and then what about the thermal energy at the end? That's a good question. That's a good discussion to have. I don't know about right here, though, in this video, at this part. We'll talk about that as soon as I'm done. All right? But do you want to show some energy going into it? Like maybe it's now thermal energy is 3. That would be okay. But the question Owen was just asking right now, if I spill some water on myself at school in the wintertime, um, my shirt will still dry. The water will evaporate. But it's not that the temperature is necessarily hotter than room temperature. I'm not going outside in the sun or anything. It's not going to be very warm outside, is it? All right, so why does that happen? All right, we'll talk about that in a sec. All right, so the next step, I got to keep track of how many blocks did I have at the start, how many blocks do I have at the end. Here at the start, I have 4 blocks. All right. And here at the end, I have a total of 7 blocks. So what happened from beginning to end? Were blocks added or blocks removed? We added how many? 3. So this gives us an idea of 3 units being transferred energy-wise, which is quite a bit. All right? Especially when we're thinking about what Owen just brought up about there not being really that much of a change in temperature, is there? All right, so we have these 3 blocks I'm going to draw. And then I'm going to put an arrow at the top of them to show that they're going into the system. I also like putting a Q. A Q illustrates that I know that this is happening, this energy transfer is happening because of a collision of particles. You've heard me say that like 6 times now in this video. Obviously, that's important for tomorrow. All right? So we understand that the water is the system and everything else is the surroundings. So that's anything that water's in contact with. Really, realistically, the glass, well, I guess when it gets spilled on your shirt, it's not a shirt, it's the air, okay? So the last thing we have to do for the quiz is you have to tell me what kind of process this is as well. Is it endothermic or exothermic? Endothermic. It is endothermic because energy is going in like N. All right? If energy was going out, we would call it exothermic. Exo like exit, going out. All right? Which would mean those blocks would have an arrow pointing the other way, energy going from the system out to the surroundings. So what's happening here? Well, we know it's because of collision of particles. We know the particles in your shirt, in the air, or both, are transferring energy to water. It's causing the water to evaporate. We can see that just by looking at the charts. It went from a liquid, 2 blocks, to a gas, 4 blocks. All right? Any questions about that?